Next is paper 2, section 1 and question 1. So see, in this he has given, there is a table, NaNO3, NaCl and AgNO3, three substances given. NaNO3, okay, then is NaCl, okay, and AgNO3. NaCl and AgNO3, like this is given. And here given is concentration in molarity. Two concentrations mentioned, 0.01 and 0.04. Like that for everyone same concentrations given, 0.01 and 0.04. So this also 0.01 and 0.04, like this concentrations mentioned. And followed by this molar conductivity at normal dilution is given. How much is the molar conductivity values given? If concentration is 0.1, it is 111 given, and concentration is 0.04, it is 101 given. Then for NaCl it is given as 117 for 0.01 and 107 for 0.04. And similarly for AgNO3, it is 125 for 0.01 and 116 for 0.04 given. Now we have to calculate what is molar conductivity at infinite dilution. We have to calculate. So how to calculate molar conductivity at infinite dilution? See, I'll do for completely NaNO3. The same thing will apply for NaCl and AgNO3. So I'm writing here for NaNO3. There is a relation which is Debye-Huckel-Onsager equation. Okay, Onsager equation. What is Onsager equation? Onsager equation is molar conductivity at any dilution is equal to a constant into root over of concentration plus molar conductivity at infinite dilution. We are going to calculate actually molar conductivity at infinite dilution. So how to calculate? I'll write molar conductivity at any dilution, how much given? 111 for 0.1 concentration. So A into root C. Concentration is given as how much? 0.01. 0.01 meaning is 10 power minus 2. So it's root if you write, or else I'll write here, which is 0.01's root. Plus we are going to calculate molar conductivity at infinite. Now 0.01's root is a perfect root. So you'll get 111 is equal to A into, this is 0.1 is the root over plus lambda infinite you will get. Let it be equation 1. Then I'll write for 0.04 concentration of NaNO3. If you write 0.04 concentration, which is given how much here? Molar conductivity is 101 and A into root over of 0.04 plus again lambda infinite we need to calculate. Now 0.04 also is a perfect root. So you can get this value is equal to 2 into 10 power minus 1. Okay, or you can write like 0.2. Okay, now 0.2 into A plus lambda infinite. Let this be equation 2. Now my aim is what? To calculate lambda infinite value. So how can I calculate lambda infinite value? This A value being unknown, I will eliminate this A value. So how to eliminate? I'll write here 2 into equation 1, and from here I'll subtract equation 2. So 2 means which is 0.01 molar concentration is there. I multiplied that with 2 and I subtracted 0.04 molar concentration from it. So if you multiply 2, it will be 111 into 2 will come, which is equal to, this is 0.2 into A plus 2 into molar conductivity at infinite dilution. This is equation 1. And equation 2 as it is you can write. 101 is equal to 0.2 into A plus lambda m infinite. So this is equation 2. If you subtract both of them, what you are going to get? So 111 into 2 will be 222. 222 minus 101 will be how much? 121 is equal to, this 2 will cancel if you subtract, and 2 lambda infinite minus lambda infinite is lambda infinite. So you got lambda infinite for NaNO3 is 121. Now the same thing I'll apply for NaCl. For NaCl also what I'm going to do is 2 into equation 1 I'll frame, okay, and minus equation 2 I'll do. Why I am going directly doing now, I am not repeating, is if you observe everyone's concentration is 0.01, 0.04, 0.01, 0.04 like that is given. So directly I am writing. So if you write like this, then you will get what here? 2 into 117, okay? 2 into 117 minus 107. This will be equal to lambda infinite, you will get. So 2 into 117 minus 107, you are going to get it as 127, which is lambda infinite for NaCl you will get. Similarly for AgNO3. For AgNO3 also I'll write same way, 2 into equation 1, okay, minus equation 2. So here how much I'm going to get? 125 into 2, okay na, minus 116. This will be lambda infinite I'll get. So 125 into 2 will be 250, 250 minus 116. So this you are going to get it as 134 is lambda infinite. This is for you will get AgNO3. So when all the three salts lambda infinite we got, now we'll proceed. Okay, so I'm erasing. So we got all the three salts lambda infinite values. We'll now proceed for calculating the alpha value. Okay, the solubility of AgCl. So see now, we got lambda infinite for NaNO3, lambda infinite for NaCl, and lambda infinite for AgNO3. These three we got. How much we got? For NaNO3 we got it as 121. For NaCl we got it as 127, and for AgNO3 we got it as 134. But he's asking is AgCl's solubility. So AgCl solubility means first we will calculate is lambda infinite for AgCl. So how to calculate this one? Is lambda m infinite AgNO3 plus lambda m infinite NaCl minus lambda m infinite NaNO3. These three if I do, I'll get AgCl's lambda infinite. So this is 134 plus 127 minus 121. So this comes out to be exactly 140. And the unit given for this one is, like Simon, centimeter square and mole inverse, like this is given. This is lambda m infinite. Now see, we know that okay, lambda m infinite is equal to 1000 into kappa divided by concentration. Okay, we need to calculate actually concentration of this is AgCl. Okay na? So concentration of AgCl if I get, from there I can get solubility. So how much will be concentration? 1000 into kappa divided by molar conductance at infinite dilution for AgCl. So we'll substitute that. So concentration of AgCl will be 1000 into K is given also is how much? K given is 1.4 into 10 power minus 6. This is also given in centimeters only. And this is divided with how much? 140. So you are going to get concentration is exactly everything will get cancelled. 10 power 5 you will get. Now given that given K, AgCl is 100% ionized. 100% ionized. Meaning is what? If AgCl is dissociating, it will give Ag plus and Cl minus 100%. So see, at time is equal to 0, we took the concentration is 10 power minus 5. Nothing is there. If it is 100% ionizing, then completely C will react, nothing will be left over. So you will get how much then? 10 power minus 5 and 10 power minus 5. This is only its solubility. How much ions produced is only solubility. And how much ions produced is 100% ionizing, which is the concentration. Right? So you can write then given is solubility. Solubility of AgCl. This is equal to S, which is equal to 10 power minus 5, which we got it as C. And this is given as how much? X given. Then asked is log of x power minus 1. So log of, if x is equal to 10 power minus 5, it's minus 1 you have to take. So minus 1 if you take, then it will be log of 10 power plus 5, and log of 10 power plus 5 is 5. That is the answer. So option C is the answer. Okay.
And has trigonal planar shape. So the bond angle here is 120 degree, and the last one NO2 minus. So in NO2 minus, the bond angle is close to 115 degree. In fact, when you draw the structure of NO2 minus, so that will be like this: N double bond O, here NO minus, and there is a lone pair. The presence of lone pair will increases the repulsion, so due to which the bond angle will reduces. So if you arrange these species in the order of bond angle, we'll get NO2 plus to be maximum, followed by NO2, then followed by NO3 minus, and the last one is NO2 minus. Hence option B will be the right answer.
Alright. Paper 2, question number 3 we are doing. Natural rubber on complete ozonolysis gives compound X as a major product. X gives positive iodoform test and toluene test. And X on heating with aqueous NaOH gives Y as the major product. What is Y? So here we are given natural rubber, which is (2-methyl 1,4-butadiene). Now natural rubber is a polymer of 1,4-butadiene, 2-methyl 1,4-butadiene. So this will automatically, we know, undergo polymerization. Alright. This is our polymerized product we will get. Alright. What will be our polymerized product? This is our polymerized product. Alright. That means this product is undergoing ozonolysis. Hence, this is our X. Now, this undergoing ozonolysis means we will break this and add oxygens. So, we will get CH2, 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 methyl and double bond O. Correct? Oh, sorry, I put an extra oxygen. We will get this. Alright. So, we will get a ketone part, and another we will get a aldehyde, sorry. Now aldehyde, we are given in the question that X is giving positive iodoform as well as toluene. Aldehyde part will give positive toluene, and this can tautomerize to methyl carbinol, which will give you positive iodoform test. Alright. Now, this is, we are told that our X is undergoing reaction with NaOH. That means it is undergoing aldol reaction. Now, how do we perform aldol? We all know that in aldol reaction, aldehyde part is more reactive compared to our ketone part. Alright. So which side will we get our carb anion? Alright. This is a molecule. These are both same. Alright. This will undergo reaction in presence of base. What will we get? We will get CH2. This hydrogen from here will be removed. H. We will get CH2 minus, CO, CH2, CH2, COOH. Now this will undergo cyclization. This carbon ion will attack the carbonyl carbon. We will get a 5-member ring. Here we have our carbonyl carbon, this one. and this pi bond will shift here, so we will get O minus. Okay, then water is provided, OH minus is removed. What are we left with? We are left with a keto hydroxy group. Now this keto hydroxy that we have formed, it can undergo dehydration, sorry. It will go dehydration. This alpha hydrogen will be removed and we will get double bond. Option A as your answer. Alright.
Here, if you observe the question, a known artificial sweetener X is composed of 4-chloro-4-deoxy alpha D galactose and 1,6 dichloro 1,6 dideoxy beta D fructose are joined by glycosidic linkage. Structure of D galactose given. Right? So, first of all, if you observe the D galactose structure, in the D galactose, at the fourth carbon, the configuration is opposite as compared to the glucose. So, first D galactose structure in the question only given. So, what is that? CHO, CH2OH, OH, H, OH, H. So, right, if you give the numbering to this compound 1, 2, 3, 4, 5, 6, this fourth carbon OH is opposite. So, that's why it is a D galactose. D galactose. And what he is telling that one 4-chloro-deoxy. That means at the fourth carbon OH is there now, O is there now, that you have to remove. That's why it is 4-deoxy. And instead of that, what we have to write? Chlorine. Then 4-deoxy, 4-chloro-galactose. Right? D galactose. This one, first of all, you have to write Haworth structure of this compound. So, if you write the Haworth structure of compound, the OH groups which are there, that one should be down, you have to write. Right side what is there, that one you have to write in down. So, if you observe the Haworth structure of this compound, right, the OH groups, this is the ring form. Haworth structure means a ring form of the 4-deoxychloro-galactose. That one you have to write. So here OH group at the bottom. Why? Alpha compound, alpha D galactose. In the alpha D galactose, OH group at the bottom. Right, remaining things as it is you have to write. How to write? These right side groups you have to write the down of the compound. Right, so 1, 2, 3, 4. At fourth position chlorine will be there. Right, at fifth position CH2OH H there. Right, this compound now we have to write in the cyclic chair form of the compound. The cyclic ring, right, cyclohexane type ring, right, so that you have to write in the chair form of the compound. In the chair form of the same compound, how to write this one? Like this manner you have to write. In this axial and equatorial forms of the bonds you have to write. This one axial bond, this is also axial bond, and this is the axial bond, this is the axial bond, and this one is the axial bond. Right, now equatorial bonds you have to write. These are the equatorial bonds. These are equatorial bonds of the compound. This one only I am going to write in the chair form. Right, so here OH is down, right, OH group. Here H will be there, H also you have to write in same manner, and give the numbering 1, 2, 3, 4. Fourth place Cl, here H. right? And fifth place CH2 OH, right? This one CH2 OH, here I am going to write here, right? Then here H, here H and OH. This is the chair form of the cyclic form of 4-deoxy 4-chlorogalactose, right? This compound react with the fructose. Which fructose? 4-chloro 4-deoxy, sorry, 1,6 dichloro 1,6 dideoxy. So first of all, you have to write the fructose structure. Which fructose? Beta fructose structure you have to write. This is the fructose structure, okay? And here beta compound, right? Beta fructose you have to write. Beta fructose you have to write means OH group should be at the up of the ring according to the ring structure of the compound, Haber structure of the compound, right? So therefore OH, this one CH2 OH actually how to write, that we will write first, later we will check it. And 1 2 3 4 5 and 6 CH2 OH. This is the sixth carbon. But what is said in the question? 1,6 dideoxy, remove oxygen atom, dideoxy. Instead of that, what we have to write? Cl you have to write. So now 1,6 dideoxy dichloro, 1,6 dichloro fructose. Which fructose? Beta fructose. Now it becomes 1,6 dideoxy and 1,6 dichloro, 1,6 dichloro beta fructose, right? Dichloro beta fructose. Here OH, H, OH, H, here H you have to take. This is the compound. When these two compounds are combined through glycosidic linkage. Through glycosidic linkage means what happened here? Loss of water molecule happened. In order to form a glycosidic linkage, there should be loss of water molecule from this compound, galactose compound, from the first carbon, which is alpha compound. Okay, alpha galactose. Alpha galactose. Which alpha galactose here? 4-deoxy 4-chloro alpha galactose compound. First carbon OH, from this carbon OH, and 1,6 dideoxy, 1,6 dichloro beta fructose, second carbon. So second carbon from this one water molecule last here from this one, then you will get a compound, we will get a new bond between this. This is the glycosidic linkage. What kind of glycosidic linkage? This one 1,2 glycosidic linkage. Glycosidic linkage. Which one? This is alpha, this is beta, right? So alpha beta 1,2 glycosidic linkage between the alpha 4-deoxy 4-chloro alpha galactose and 1,6 dideoxy 1,6 dichloro beta fructose. So the option C is correct answer. Understood, students?